Hello there, amazing people, students, subscribers, and all the lovers of chemistry out there. I'm super excited to be here with you today on this next episode that we've been looking at on this series of Gauss Law. So, today we want to look at the concept of the Charles Law among the three major gas laws. We've looked at the Boyle's Law, so this is the second in the series, the Charles Law. Now, the Charles Law is the law that talks about the relationship that exists between volume and temperature when pressure is kept constant. So let's go into what we have for today's video. So it's important to note that the Charles Law shows the relationship that exists between volume V and temperature T of a gas when pressure is kept constant. Remember, I said it before, but I'll say it again because it's very important for you to bear this in mind. That when we're talking about the gaseous state of matter, there are many variables you need to be very, very familiar with. You need to be familiar with the concept of volume. You need to be familiar with the concept of pressure. You need to be familiar with the concept of temperature for a start. Now, this law called the Charles Law talks about the relationship that exists between two out of those three variables that we just talked about. The variables called volume and temperature when pressure is kept constant. So what does this law say? It states that when pressure is kept constant, the volume of a gas is directly proportional to its absolute temperature. So if we want to write this out mathematically, volume V is directly proportional to T, which is its absolute temperature. I'm sure you're seeing how everything is playing out. What does this mean? It means that if volume is directly proportional to temperature, anything that happens to volume must happen to the temperature. So it means if volume goes up, the temperature must also go up. And if the temperature goes down, it means the volume must also go down as well. And we're going to see how each and every one of these will play out as we solve some questions in the examples contained in this video. So the key idea when you're dealing with the Charles Law is to note that when you heat a gas, you are increasing its temperature. So that makes the volume to increase because that gas will surely expand, which is a very good explanation for what happens when you keep a football on a concrete platform and then maybe the sun is high. You would notice that after a while that ball becomes as though it were pumped using an air pump. It's not like the ball was pumped using an air pump, no, but it's because the temperature has increased. Therefore, the gas particles contained in that ball are now beginning to expand, which makes the volume of that ball to increase. When you cool a gas, on the other hand, it shrinks and the volume reduces, which is a very good explanation for what happens to your soda cans when you place them in the fridge. After a while, it looks as if the can wants to begin to get squeezed, and if care is not taken, it can burst open. So in the Charles Law, it is a direct relationship between volume and temperatures. Both values move in the same direction. Now let's look at some examples to buttress what we have just said. The first example is the example of the hot air balloon. Most of you may have seen this in movies. I've never seen one up front in real life myself. I've seen hot air balloons in movies. Now you can see in the hot air balloons there is a position at the bottom where fire is being generated, and the importance or the application of that fire is to increase the temperature of the air that is contained in the balloon over here. And when that happens, the hotter that gas or that air gets in the balloon, the more the volume that air will occupy, which is why it looks as though, or which is why this balloon here is expanding. So what's happening in the hot air balloon is that when the air inside is heated, it expands and it makes the balloon to rise and float in the air. So whenever they want to land the hot air balloon, what they do is that they reduce the intensity of the heat that is being applied. So that will make the volume to reduce and the balloon to come down. That being said, let's move on to the next example. The next example of the application of Charles' law is the example of your car tires. You see, on a hot day, when your car is parked, let's say inside the sun, the air inside your car tire tube begins to expand, which increases the tire pressure and the volume that it occupies. The same thing also happens to your balls that you keep in the sun. After a while, it looks as if the ball has increased in size because of the increase in temperature. Third example that we have is the example of your soda cans that are kept in the freezer. You will understand that after a while, when the freezer becomes extremely cold, the cool air begins to contract and then it reduces the volume. And after a while, the can now gets crushed and then the content of the can now begins to spill out because of the reduction in temperature. So now here is the formula when we're dealing with the Charles law. V1 divided by T1 is equal to V2 divided by T2. Now, how did we come about this formula? I will show you. From the statement of the Charles law, it states that the volume of an amount of gas is directly proportional to its temperature. So if we want to convert this sign of proportionality into an equality sign, we need to introduce a constant, K. When we do, it now becomes V is equal to KT. So now, if we want to make K the subject of the formula, it now becomes V all over T is equal to K. So this means that the value of volume divided by temperature will always be constant in the Charles law. So that means V1 over T1 is equal to V2 all over T2, which will be equal to V3 over T3, and so on and so forth. Now, V1 stands for the initial volume, T1 stands for the initial temperature, V2 stands for the final volume, and T2 stands for the final temperature. So now that we know what the variables mean, let's see if we can do justice to a few questions. Question number 1. A gas has a volume of 2.0 liters at a temperature of 27 degrees Celsius. What will be the volume if the temperature is increased to 127 degrees Celsius? Assume that the pressure is kept constant. So let's go ahead and list out our variables. First thing they said is a gas has a volume of 2.0 liters. So V1 is equal to 2.0 liters. At 27 degrees Celsius, T1 is equal to 27 degrees Celsius. Now note, when we're dealing with gas laws, we do not measure temperature in degrees Celsius. We measure it in degree Kelvin. And when you want to convert from degrees Celsius to degree Kelvin, you add 273. So here we have 27. So to convert it to degrees Kelvin, we'll add 273. This gives us 300 degrees Kelvin. Now that we've done that, they are asking us what will the volume be. So V2 is unknown, which is the final volume. If the temperature is increased, T2 is 127 degrees Celsius. So let's convert this into Kelvin as well. To convert into Kelvin, we have plus 273, which gives us 400 degree Kelvin. So now that we have all our variables, let's impute it into our formula that says V1 over T1 is equal to V2 over T2. V1 is 2.0 divided by T1. T1 is 300 is equal to V2 is unknown divided by T2, which is 400. So at this point, we can cross multiply. If we do, it becomes 300 times V2 is equal to 400 multiplied by 2. So we have 300 V2 being equal to 800. So at this point now, we can now calculate the value of V2 by dividing both sides with the coefficient, which is 300. So 300 cancels 300. V2 now is equal to 800 divided by 300. 800 divided by 300 gives us 2.667. 2.667 liters, because that's what volume was measured in. So you can see in this case, temperature increased from 300 Kelvin to 400 Kelvin. And the same thing happened for volume. It increased from 2.0 to 2.667. Now we can do a bit of math to get to check if we are correct. We need to, how do we do that? We'll simply impute our variables into this formula over here. And if the left side of the equation is equal to the right side, it means that we solved this question correctly. So let's do that very quickly. For V1 T1 being equal to V2 T2, V1 is equal to 2.0 and T1 is equal to 300. V2 is equal to 2.667 and T2 is equal to 400. 2 divided by 300 gives us 0.006. 2.667 divided by 400 gives us the same thing, 0.006. So you can see that we solved this question correctly and it obeys the Charles law. So let's move on to the next example. The next example says a balloon has a volume of 4.5 liters. V1 is 4.5 liters. At 77 degrees Celsius, T1 is 77 degrees Celsius. So plus 273, that gives us 77 plus 273, that gives us 350 degrees Kelvin. What will be its volume? V2 is unknown at 0 degrees Celsius. T2 is 0 degrees Celsius, which is plus 273, that is 273 degrees Kelvin. So let's impute our variables into the equation. V1 over T1 is equal to V2 over T2. So V1 is equal to 4.5. T1 is 350. This is equal to V2, which is unknown, divided by T2, which is 273. At this point, we cross multiply. It now becomes V2 times 350 is equal to 4.5 times 273. So this multiplied by this, 4.5 multiplied by 273 is equal to 1228.5. So V2 multiplied by 350 is equal to 1228.5. So we can calculate for V2 by dividing both sides using 350. So V2 is equal to 1228.5 divided by 350. If we punch our calculators, divided by 350, that gives us V2 is equal to 3.51. So you can see volume has reduced from 4.5 all the way to 3.51, and temperature as well also reduced from 350 to 273 Kelvin. So you can see how the Charles law applies to this question. So let's move on to the next thing on our list. And the next thing on our agenda are some practice questions that I want you to try out your hands on, and you can comment the answers in the comment section below and I'll be more than willing to receive them. First question says a gas occupies a volume of 3.0 liters at 17 degrees Celsius. What is the volume at 87 degrees Celsius? The next question says a gas has a volume of 6.0 liters at 373 Kelvin. What is the volume at 273 Kelvin? So go ahead, do justice to those questions and let me have your answers in the comment section. So it's bye for now. We've looked at the Boyle's law in the previous video, and now we've looked at Charles' law. So up until I come your way next time, where we'll be looking at more laws and diving deeper into gas laws. My name is David, and all we do here is to take the mystery out of chemistry so chemi can make history. I will surely see you in the next video.